Hello everyone! In the study of probability, we know that when two events A and B are independent of each other, the probability of the product event is equal to the product of the probabilities. How to calculate the probability of the product event AB if events A and B are not independent of each other? Is there also a general formula? Let's start with specific situations below. Let's do a statistics on site, collect data, and complete this form. There are a total of 45 students in the class, including 25 boys, 20 girls, 30 members, 15 non-members, 16 member boys, 9 non-members, 14 member girls, and 6 non-members. The data has been collected. Now let's look at problem 1. Randomly select one person from the class as a representative and calculate the probability of the following event. Please complete it independently. Randomly selecting one person as a representative, the sample space omega contains 45 sample points. To calculate the probability of a random event, it is necessary to represent the random event with symbols. If A represents the event selecting a member and B represents the event selecting a boy, then N omega equals 45 and A equals 30 and B equals 25. According to classical conceptual knowledge, the probability of selecting a member is 2/3. The probability of selecting a boy is 5/9. The probability of being selected as both a member and a male is 16/45. If it is known that the selected member is a member, what is the probability of selecting a male member? Can you give me a reason? The answer is 8/15. This is equivalent to selecting male members among the group members, reducing the space to 30 people, and using classical probability calculation formula. The probability is 16/30th, simplified to 8/15. The probability of selecting a male member under the condition of selecting a member is denoted by the symbol for the probability of event B occurring under the condition of event A. Read as the probability of event B occurring under the condition that event A occurs. At this point, it is equivalent to considering the probability of event B occurring using as the sample space. In the new sample space, event B is the set of events AB containing a sample point count of N of B. It can be visually represented by this table. According to the knowledge of classical models, under the condition that event A occurs, the probability of event B occurring is equal to NAB divided by NA, which is 8/15. Follow-up 1. What is the reason why the results obtained from 3 and 4 are different? Question 3 is to consider the probability of event B occurring in the entire sample space, while question 4 is to consider the probability of event B occurring in event A in the new sample space. The occurrence of event A reduced the sample space, and considering that the sample space for events 3 and 4 is different, the results are naturally different. Follow-up 2. Why does the molecule use NAB instead of NB in the calculation formula of 4? Because in the new sample space A, event B is the product event AB, so the number of sample points is N of B. Through the specific example of question 1, we can intuitively perceive that under the condition of event occurring, the sample space will be reduced. The essence of conditional probability is the probability of event AB in the new sample space A. Calculate in this way. Can you explore the relationship between the probability of event B occurring and PAPB and PAB under the condition that event A occurs, based on question 1 and figure 1? If event A is known to occur, then it becomes the sample space, and the probability of event B occurring is the ratio of the number of sample points contained in event AB to the number of sample points contained in A, that is, NAB divided by NA. From this equation, it can be inferred that, so under the condition that event A occurs, the probability of event B occurring can also be calculated by dividing PAB by PA. From this, the definition of conditional probability can be obtained. Through the analysis of problem 2 and the intuitive perception of figure 1, the definition of conditional probability is no longer limited to classical models, and is applicable to general probability models. In both question 1 and question 2, we found that they are not equal. If they are equal, what conditions should events A and B meet? When events A and B are independent of each other, because the occurrence of event A does not affect the probability of event B occurring, under the condition that event A occurs, the probability of event B occurring is equal to PB. We can also verify our intuitive conjecture through rigorous proof. If events A and B are independent of each other, under the condition that event A occurs, the probability of event B occurring is equal to PB, and vice versa. So, if and only if A and B are independent, they are equal. Follow-up question 1. If events A and B are not independent, how to calculate the probability of event B occurring under the condition that PA and event A occur? How to calculate PAB for any two events A and B? By deforming the conditional probability formula, the formula for calculating PAB can be obtained. Transforming the conditional probability formula to obtain the probability formula for any two events A and B, as well as the event itself, is called the multiplication formula of probabilities. If PB is greater than 0, then PAB can also be equal to the product of PB and the probability of event occurring under the condition that event B occurs. Let's take a look at an example. The meaning of not putting the extracted questions back is that if we consider the first extraction to an algebra problem and the second extraction to a geometry problem as two separate events, since the extracted questions are no longer put back, the two events are not independent. So, problem 1 is the probability of the product event, and problem 2 is the conditional probability. You can first calculate the probability of the event and then use the conditional probability formula to calculate the conditional probability. You can also first calculate the conditional probability and then use the multiplication formula to integrate the probabilities of events. To calculate the probability of a random event, it is necessary to represent it with symbols. Let A represent the first algebraic problem drawn, and B represent the second geometric problem drawn. Solution 1. The first time I drew an algebra problem and the second time I drew a geometry problem was the product event AB. Randomly select 2 experimental sample spaces from each of the 5 questions without putting them back. The omega contains 20 equally possible sample points, which means the probability of the set event is 3/10. The probability of drawing an algebra problem for the first time and a geometry problem for the second time is the probability of event B occurring under the condition that event A occurs. It can be obtained using the conditional probability formula. Solution 2. Find the conditional probability on the reduced sample space A. Given that the algebra question was drawn for the first time, there are still 4 questions left, including 2 algebra questions and 2 geometry questions. Therefore, under the condition that event A occurs, the probability of event B occurring is 1/2. Also, because PA is equal to 3/5, the probability of the set event can be obtained as 3/10 using the multiplication formula. Follow-up question. What are the general methods for calculating conditional probabilities based on the above example questions? One approach is to first calculate PA and PAB based on the sample space omega, and then use the conditional probability formula to calculate the probability of event B occurring under the condition that event A occurs. Another approach is based on the intuitive meaning of conditional probability, where the condition for A to occur is added and the sample space is reduced to A. The probability of event B occurring under the condition of event A is calculated using as the sample space to calculate the probability of a B. The first type is based on the sample space omega and is mainly applicable to general models, while the second type is based on the intuitive meaning of conditional probability and is mainly applicable to classical models. Question 2. What do you think are the properties of conditional probability? Through the previous learning, we understand that conditional probability only reduces the sample space, and we think it should have the same properties as the probability we learned before. Conditional probability also has properties similar to probability, such as non-negativity, normativity, additivity, probability of opposing events, uniqueness, and so on. Review the content of this lesson and answer the following questions. Given the conditions under which event A occurs, the probability of event B occurring is the conditional probability. The sample space considered for conditional probability and product event probability is different. The conditional probability is larger, and there are generally 2 methods. One is based on the entire sample space, and the other is to calculate the conditional probability in a reduced sample space, which has the same property of probability. The conditional probability and the probability of the set event are understood and calculated separately from different sample spaces, and are both related to the set event AB, which must be interrelated in the formula. Due to the known conditions under which event A occurs, the probability of event B occurring is equal to PAB divided by PA, which is greater than or equal to 0 and less than or equal to 1. Therefore, under the conditions under which event A occurs, the probability of event B occurring is greater than or equal to PAB. We can use the conditional probability formula to calculate the conditional probability. Or we can use the general understanding of conditional probability to calculate it using classical probability models on a reduced sample space A. As a special form of probability, conditional probability must satisfy the properties of general probability in sample space A, such as the non-negativity and normativity of probability, the addition formula of replicated events, and the sum of probabilities of opposite events being 1. With these properties, when solving complex problems, an event can be divided into different categories and calculated using conditional probabilities. That's all for today's class. Goodbye, everyone.